Hi, I'm Dr. Jerry Tanny, and I'm here to talk again about analyzing rocks that have been found at sites where UFO activity was observed. My earlier film dealt with a sample found by Dan Jacoby at Kadima, in a field not far from his home. Since then, David Ronen gave me a second sample found at a different site and date in Kadima, and another one found at the Ramon crater in the middle of the Negev, and a third sample found at Mount Harif, also in the Negev, on the border with Sinai. David Ronen's samples were also analyzed, and the purpose of this film is to bring together all the data on the 4 samples. Relevant sections of my earlier film have been included in what you are about to see. Professor Aaron Katsir of the Weizmann Institute began many of his lectures by saying that if you can't tell the story logically, at least you can tell it chronologically. Well, for the most part, I'm going to try and use that approach. A few words of introduction about myself, for those of you who never saw my first film. After receiving my PhD in chemistry from McGill University, I spent 10 years at the Weizmann Institute in Rehovot, Israel, and then moved on to work in industry and in Israel and in the United States. After retiring from HP Indigo in 2012, I began a new career as a director of documentary films. That's how I met Dan Jacoby, a resident of Kadima, and a member of MUFON Israel. And this is when I decided to make a film about UFOs in Israel.
9 למרץ 1994 קיבלנו ידיעה מחבר שלנו שהוא טייס אולטרלייט חובב, שהוא הסתובב כאן באזור וראה עיגול נחיתה. העיגול הוא בערך ליד השיח שמה לפני עץ האקליפטוס. ובאנו לכאן, קבוצה של חוקרים, להתחיל לבדוק מה הולך כאן. מצאנו עיגול נחיתה קלאסי בקוטר של 12 מטר. היו כאן ממצאים נוספים, אתה יכול להסתכל על התיק שלי, אני פותח אותו. ברבים מאתרי הנחיתה בקדימה מצאנו אבנים כאלה. אפשר להסתכל מקרוב. זאת אבן שבדקנו והיא עשויה בסיליקון. ברבים מהאתרים היו אבנים כאלה בכמויות משתנות. עם הזמן היו כאן נחיתות נוספות. עוד 4-5 נחיתות בדיוק באותו שטח.
Dan found many such rocks at different sites over the years. An analysis that he had performed at the Technion at the time on a similar looking rock showed that it was very pure silicon. He gave me the large one that you saw in the film for further analysis using a scanning electron microscope. To use the SEM, we needed to cut a small piece off of the Dan's rock. Now, because of silicon's hardness, a diamond disc saw is required to do the job. Fortunately, Yair Ashkenazi, the glassblower at the Weizmann Institute, was willing to help out. As long as we're on the subject of the rock's hardness, let me digress from the chronological story to show you some new data on Dan's sample from work by a friend of mine, Professor Sidney Cohn of the Weizmann Institute. He measured the modulus and hardness of Dan's sample by a technique called nanoindentation. These graphs are the data from his measurements. You can see from this table that the values he found are at the high end of the range for pure silicon. Now, silicon exists in 2 crystallographic forms, the 100 and the 111 form. We won't bother about what these crystallographic names mean, But the point is that Dan's Kadima sample is at the very high end of the range for crystalline silicon consistent with what is called the 111 form. Now, if we look at a comparison of the characteristics and uses of the two forms, the 111 form is primarily used for power and RF applications and also as a resonator. We will return to this point at the end of the film with some new data that I'd like to show you. Before we move on to the topic of scanning electron microscopy, I also want to examine the property of heat transport that these samples have. Many of you have seen in clips of ice melting rapidly on rocks like these. And most people are unaware that pure silicon has an intrinsic rate of heat transport that is higher than iron and only below copper and aluminum. Because we cut Dan's rock with a diamond saw, we have a nice smooth surface on which to do a simple experiment to measure the heat transport rate of this sample. Now, I've made this schematic to better explain our experiment. We place the rock in a bath of water at room temperature of 25 degrees, and that's so that we now have a bath that gives us a heat sink. And we measure in centimeters the distance from the surface of the water in the bath, in this case 4.5 centimeters, to the nice smooth surface that we have cut on the rock. Now, by measuring the 3 dimensions of the ice cube, we can get the volume and therefore the weight of the ice to be melted, in this case about 32 grams. And also we can measure we have the contact area between the rock and the ice, which is 4.5 square centimeters. So we start the timer on your phone and we get the time of melting the ice. Now, I had to put a plastic ruler in place here to prevent the ice cube from moving around off the rock, basically because little air bubbles in the ice cube are released when the ice melts and makes the cube move around. Those little air bubbles come when you freeze the ice because there's gas dissolved in the water that was used to make the ice. And of course, ideally, we should have, say, boiled the water before putting it in the ice cube container to make the ice cube. In any case, using equations for heat transport and the above data, we can also calculate the time needed to melt the ice cube, assuming that it's the same as pure silicon. The calculation comes out as 4 minutes and 45 seconds. I had to stop the experiment before the ice completely melted at 4 minutes and 25 seconds because the surface area of the ice at the bottom in contact with the rock was contracting and was no longer 4.5 square centimeters. But in any case, it's clear that the rock's rate of heat conduction is in the same ballpark as that of the pure silicon. Okay, so now back to the SEM work on Dan's Kadima sample. I'm going to use clips from the earlier film. The next step was to order 2 hours of SEM time with Dr. Einat Zellinger at the Center for Scientific Imaging in the Faculty of Agriculture of the Hebrew University in Rehovot. Einat attaches the sample to the base with conductive tape, and we are ready to go to the scanning electron microscope. After inserting the rock sample, she turns on the pumps for evacuation of the chamber, and we get our first look at the material. The diamond disk has mashed the surface, making it relatively featureless. The white line in the box on the bottom shows the length of 0.05 centimeters in the picture. We find a hole in the surface with a crystal in its depth. A knot raises the magnification so that the white line now represents 0.002 centimeters, and we analyze the elements present in the area of the little yellow box up above. The analysis comes back. As you can see in the black box below, the crystal is 98.9% silicon and 1.1% indium. We go back to low magnification and analyze the surface. This time the answer comes back with 1.2% oxygen in addition to 97.5% silicon and 1.2% indium. So Dan's sample certainly isn't metallurgical silicon that can be bought on the internet. Now, although the indium concentration is about double the maximum normally used in silicon doped with indium, that combination is known in the semiconductor industry for infrared light sensors. Then a few days later, our analysis fell apart. At the suggestion of a geologist friend in the department, a knot examined the sample in an optical microscope that illuminates the surface with 3 different wavelengths of ultraviolet light and shows fluorescence in the presence of certain elements. Although a low concentration of indium in silicon should not show any fluorescence, Dan's sample lit up like the night sky when illuminated with all 3 wavelengths. So, just to be clear, based on our original SEM results, this black picture from EVOS examination of a sample of pure silicon that's used for calibration of the SEM, this is what we really expected to see based on our first SEM results. Where had we gone wrong? We had ignored the Lanthanide family of rare elements. In order to save analysis time, the SEM's program ignores the Lanthanide elements unless you specifically request to examine for their presence. So we marked the area analyzed in the UV microscope with some dots with a pen so that we could identify that area in the SEM, and then redid the elemental analysis at low magnification with the lanthanides requested this time. 13 of the 14 members of the Lanthanide family showed up with a cumulative weight percent of almost 38%. I've created these separate tables from the original results because of the difficulty in reading them in the original table. Amongst the lanthanide elements found is 4% thulium, which has a value of $3,000 per kilogram. The non-lanthanides present are 2% oxygen, 8% carbon, 51.7% silicon, and 0.29% indium. The low oxygen content is very significant because it means that virtually all of the lanthanide metals are in the pure state, as opposed to oxides or salts that are normally found in nature. We moved to a new silver-looking area that had small crystals. It showed only 0.29% of lanthanum and 2.8% of ytterbium, with large amounts of iron and titanium. The composition varies considerably at different spots and is not homogeneous. Once again, the metals must largely be present in their pure form because the oxygen concentration is too low for all of the metals to be present as oxides. The heterogeneity of the rock composition is like that found in meteorites. However, the elemental composition has nothing in common with those normally found. Note the high oxygen content of meteorites. In addition, the lanthanide family content of meteorites is the order of hundreds of parts per million, and not up to 6% as in Dan's material. David Ronen is a well-known Israeli ufologist who has also found rock samples at the UFO sites, and he gave me those samples that I told you about earlier after seeing my results on Dan's Kadima rock. For those of you who haven't seen the original film, I'm going to let David tell the story about how he found the sample at מכתש רמון.
את האבן הזאת אני מצאתי באזור שקרוב למכתש רמון. אני קיבלתי לפני כחצי שנה עשרות טלפונים מחיילים היסטריים שבחרו לי בטלפון. מסתבר שהם היו במסע ניווטים, באור יום, ופתאום ראו דיסק ענק, כסוף, עם בטן ועם גיבנת כזאת, גולש מעבר לגבעה הסמוכה אליהם, ונעלם, וכעבור 2-3 שניות ממריא למעלה. לקחתי את קבוצה של מדענים, הגענו לאותה גבעה שהחיילים תיארו לי היכן היא נמצאת. וקודם כל, הדבר הראשון שמצאנו זו פלטה ענקית של זכוכית, שנוצרה כתוצאה מחום עצום שהוקרן כלפי מטה. מצאנו גם את האבן הזאת, ועוד 3 בגודל הזה, והיו שם עוד אלפים קטנטנות, ממש בגודל של ציפור.
SEM pictures at high magnification of the samples for all 3 sites are similar really to one another and to Dan's sample from Kadima, with no defining special features visible. The EVOS microscope showed response, but only in the blue region. As you can see from this summary table of the SEMs at high magnification, all the samples are quite similar in chemical composition. They're all 99.5% pure silicon with about 0.2% of indium and another 0.2% of Ytterbium, and all 4 samples have similar values. Indium dissolved in pure silicon converts elemental silicon into a p-type semiconductor. And the additional presence of the rare earth ytterbium element is also significant in this regard. As this table shows, rare earth elements are doped into silicon to create a wide variety of sophisticated semiconductor devices. This is similar to what I said in the earlier film when we only had Dan's sample. So now you may feel confused and ask me, how are we supposed to understand these different analyses from the SEM on Dan's samples that show 99.5% the pure silicon at high magnification, and sometimes only 51% when we do it at low magnification of the type of the level, let's say, that the EVOS microscope is magnifying. The best analogy that I can give you is something like this. If we were to be looking at the Earth's surface from very far away, and the Earth's surface is about 70% covered by water. So if you were at a distance that you couldn't really see the Earth, and you randomly measured the composition of, say, just a few square meters of the Earth's surface, there's a high probability that you would come back with a measurement that says that the Earth is just salt water. Now, if you measured the Earth's surface composition at very low magnification, so that you were taking in millions of square meters, then you would also find the elements associated with land, like silicon and all the rest of the elements that we know are associated with the composition of the Earth. And that's exactly what happened with our use of the scanning electron microscope. When we are first doing the SEMs, if we don't see any kind of structure that looks significant, the immediate impulse is to go to very high magnification. So that's where we got the 99.5% the silicon numbers. It wasn't until we used the EVOS microscope, which looks at low magnification, we didn't know where to look for the other elements. Our high magnification SEMs are on random, very small areas, like the ocean salt water in my analogy. The EVOS microscope showed us the existence of the islands of all the other elements that are distributed in this quote-unquote ocean of the pure silicon. Now, the analysis of rocks from 4 different sites so far hasn't helped us answer the question as to their purpose, that is to say, why these rocks were found at these sites on the ground. However, at least it does show that their similarity and something about the consistency of whatever technology created them. Before we sum up everything we've learned, I promised some new information, which I received from Mr. Alon Pedut on an experiment he did in a friend's house on a sample that he received similar to mine from Dan Jacoby.
Still safe. Okay, let's try the rock. Ooh. It has radio frequency. It's interesting. Safe though. Safe as you. Oh! No! What is this? Oh my God! What just happened?
Okay, the EMF device that you see that he used in that clip is called a Habotest 627, which can detect RF signals between 5 to 50 gigahertz. Unfortunately, it does not indicate the frequency of whatever signals you pick up with the device. But one thing is for certain, the signal of 17 to 19 milliwatts per square meter that you saw in the clip is real. When Alon tried to repeat the experiment outside or in his own house, no such signal was seen. And this shows that the signal that he saw in the house was associated with some signal in his friend's house, probably the very high, fast 5 gigahertz Wi-Fi. And the source of this RF is not within the rock itself. So let's look back at that slide on the likely crystallography of the silicon that we found based on the mechanical modulus and the hardness. The 111 form is used for applications in RF and resonators. Now, this would fit very well with these latest observations with that Habotest 627 device. Clearly, we need to do more work on the electrical properties of these rocks. Finally, artificial intelligence is all of the rage these days. I use ChatGPT 4.0 to help with my research on thermal transmission and the silicon properties. And then I got the idea that I would feed all of the data on the samples into ChatGPT and ask for an assessment. I have to admit that I was surprised by how very coherent a report it gave me back. And I just thought that it was worth showing you what it had to say about all the data that we found to date and what we might do more to experiment on these samples to give us further information. So there you have it. If we can find the funds to do so, we will try to do more SEM work on additional samples. I hope you found this film interesting, although those of you with a limited background in chemistry no doubt found it challenging. Anyone interested in contacting me is welcome to send me an email at the address shown below.